right, so for the last talk of the morning session, we'll have Alex Suciu, who will talk about resonance schemes of simplicial complexes.
Thank you very much for the introduction. It's such a pleasure to be here and see many old friends and meet new people. Okay, so first of all, I mentioned that this is joint work with Mariana Produ and Gabi Farkas and Claudio Raicu, and also this Samartano, who kind of joined this. So this is part of a bigger project. I kind of listed this paper. So we started with this one, which I'm still trying to finish, and hopefully we're going to talk later this year, the different conference. And I'll talk a little bit about this one that kind of splitting from the bottom up. And then finally, we got this where Samartano joined us. And this is actually about having quite a bit to do with the subject of the conference. Okay, so. But let me start with the general context here. It's in the title of the talk, is resonance varieties. Many of you have heard me talk about these gadgets before. So I'll start with graded algebra, graded commutative algebra over a field of characteristics 0 to make things easy today. So think of you're going to get, sorry, at some point to the Steiner-Reisner ring of a simplicial complex. So if you don't want to think in too much generality, just think for now with the exterior Steiner-Reisner ring, okay? And I want it to be connected. It's just the scalars in degree 0, and every graded piece is finite dimensional. And I'm focusing now in degree 1. So if you have a class in degree 1, A cap A is minus A cap A, so A squared equals 0 because varying characteristics not equal to 2. So multiplication by A defines a cochain complex on A, okay? So you turn this algebra into a cochain complex with differentials given by left multiplication by A, where A is an arbitrary element in A1. So the parameter space here is A1. And the jump loci, so what are these jump loci? You look at the elements A in A1 for which the cohomology of this cochain complex does not vanish in degree I, okay? So you can do also by how much it jumps, and there's some kind of all sorts of variations on this theme, but to keep things concrete, I'm just going to have a single index here. Is the homological index, okay? So, and actually these algebraic varieties, I'll try to convince you on the next slides of that, but in degree 0, that's not very interesting, it's just 0. In degree 1 already it's an interesting variety. More concretely, you can think of it as being, okay, so what does it mean to be a cos cycle here in degree 1? There is a B such that AB equal 0 in A. So what does it mean? It means it belongs to the kernel of the multiplication map from A1 wedge A1 to A2. And I'm also throwing in 0 just to make sure to have it there, okay? I'm assuming that A1 is not equal to 0 for that. All right, so how to provide equations for these varieties? So this goes through this classical Bernstein-Gelfand correspondence. So I'll pick a basis E1, En for A1, okay? If you like, I mean, this is the M we've seen before, but I cannot bring myself. For me, the number is N. And then dual basis, so I'm going to lower the indices by taking K duals, okay? So X1, Xn is a dual basis. And then I'm going to identify the symmetric algebra of a lower one with S, the polynomial ring in variables X1, Xn, which I think of as being the coordinate ring of the affine space A upper one, okay? So it's just a big peak basis and you have coordinates, okay? And then I'm going to form a Koszul complex, which you can think of as being, done by in a categorical way through this BGG correspondence that takes as input this A, and it spits out a cochain complex now of finitely generated 3 S modules by taking in each degree A tensor S, and the differentials are given by, and I think you've seen them, I think Taras, right, or some talk many people talk about some kind of version of this causal. Well, it goes back to causal. You multiply by the e's on the algebra side, and by the xj by the x's on the polynomial side. Okay. And that's actually the delta square equals 0. You check that easily because anti-commutativity on one side, commutativity on the other side. And then if you specialize, if you give values to at the element a equal in a1, right? I mean, if you just set the xj equal to aj, basically, you get back this cochain complex that we had on the previous slide, right? This is just, instead of having just one for each a, now you have a globally defined. But before, let me just kind of draw you a comparison, attention. So here, this was a chain complex of finite dimensional k vector spaces, right? So the boundary maps are just matrices, matrices with entries in k. Here, the boundary maps are matrices with entries in S. But, the entries are linear forms in the variables xj. Okay, and then, all right, and here's a little lemma that A is in A1. When does an element resonate? When is it the resonance? When, so chain complexes like to be exact, right? Generically they're exact, but there are some places where the cohomology jumps, right? These are these jump loci. And then you write down this rank condition on these differentials, and you want this rank to be less than bi of a, the rank of ai. And therefore, if you work it out here, what this means, it's a variety defined by the vanishing of certain minus of a certain size of these matrices with entries in the polynomial ring S. So it defines a variety as the zero locus of these fitting ideals. And I'm going to get in a little while about also the scheme structure, you see, but this is not the scheme structure I'm going to use. This is a kind of a nasty one. It's useful in each, depending on which situation you are interested. But we'll use a different scheme structure than this one given by these fitting ideals. Okay, so it's on this slide. Let's dualize now this causal complex. Okay, so now it becomes a chain complex, also S module. So basically, you just take transpose, you transpose all these matrices, okay, in down to earth terms. And you take the homology of this chain complex, okay? Call it Wi of A. So I call them the causal modules. And they have all sorts of names. I mean, initially, they're more like also sometimes in topology, you call them, it's a kind of a linearized version or infinitesimal version of some Alexander modules, like in knot theory and low-dimensional topology. The motivation comes from topology. But anyhow, it's the homology modules. So they're graded S modules associated to algebra A. In degree 1, you can actually find an explicit finite presentation of this module as such. Remember, we had this K, which was the kernel of the multiplication map. You can take K perp, which is the functionals on lambda of A1, which vanish on K. So that's now a subvector space of A1 wedge A1, which is E2. What is E? E is the exterior algebra on A1. And again, by taking duals, I lower the degree, okay? So anyhow, what is this? This is the classical, again, this is the causal differential from E3 tensor S to E2 tensor S, right? Or the transpose of the other causal differential. And this is just an inclusion map. Okay, so that's the presentation, it turns out. For technical reason, I added these slides because at some point on the last slide, I was kind of thinking of one of the lectures today, and I wanted to add some stuff. So you can actually do this in generalize this setup and find the presentation if you put some more restrictions on, okay, so on this algebra. Up to now, the algebra was basically arbitrary, right? So let's take a little bit of a different point of view. You fix some integers d and n, you take v to be an n-dimensional vector space, and you just take a subspace in the exterior power of v, d plus 1 exterior power, okay? And you set S to be the symmetric algebra, E is the exterior algebra on the dual. K perp, again, it's the dual of lambda d plus 1 of v mod k. And you set A to be, instead of an arbitrary one, you take the exterior algebra modulo this ideal generated by K perp. So you see, it's the generators are in a fixed degree. It's a homogeneous kind of, it's E divided by homogeneous ideal. And if you take now the inclusion of A, so there is a projection for E upper star to A upper star, and then you dualize if you get an inclusion. And then it turns out that these causal modules vanish up to some degree. And in WD, which is now the generalization from D equal 1 before, again, you have a presentation of the same sort. But in general, I don't have a presentation for this module that I can write down in absolute generality. Okay. So that's okay. So let's talk about the resonance, the scheme structure. That comes up in the title of my talk. I'm going to talk now. I'm going to view this the resonance scheme as being the spectrum of S modulo the annihilator of Wi of A. Okay. So this is a module. You take the annihilator, and so in other words, as a set, you view Ri, you see, but now there is a different index. I put it down here, okay? I'm taking now the support varieties of these causal modules, okay? And they come with this scheme structure, naturally, the annihilator ideal of these modules. And then there is a relationship between this jump, I call this the jump loci. They came from homology jumps, right? And these are the support loci. Let's go jump loci versus support loci. In degree 1, they agree as sets, but in higher degree, I mean, I did this some 10 years ago with Papadima. We proved this, generalizes some previous results, that in a filtered way, these varieties coincide, but not on the nose in general. And I'll come back to this. Okay, so to recap, we have like two sets of varieties, resonance and support loci, two kind of scheme structures. And okay, so that's some pretty abstract algebraic definitions. I'll kind of maybe not say too much about this. This is from like the middle paper I was telling you about, with some motivation having to do with Chandran conjecture, other things. But in terms of this R upper 1 of A, we can talk about a linear subspace to be isotropic with respect to K if L wedge L is in K. Separable if some kind of condition happens that if the intersection, it will take the ideal generated by L inside the exterior algebra, intersect with K. If that's contained in L wedge L, then you call the subspace separable. So there are some kind of conditions having to do with how this K sits inside A1 and wedge A1. And these are kind of the extreme cases. If K equals 0, then everything is separable. If K is everything, every subspace is isotropic, but only the trivial one is separable. Here's a simple example. We take the exterior algebra, modulo this idea, modulo the ideal generated by these two vectors. And then the resonance is the span of E1 and E2, which is isotropic. You see the wedge is inside K, but it's not separable because these are multiples of E1 and E2, so they lie in K, but they don't lie in wedge 2 of L, which is just E1 and E2. So you have this extra guy which doesn't lie there. So, okay, so all right, so what does this have to do with anything? These are a bunch of definitions. Okay, just a slide about this result. All right, so let's take the composition of this resonance variety in irreducible components. And then we have this kind of local subspaces. You take K intersect Lj with a wedge Lj. And then in the same way, we define this with the presentation, right? See, let me just go back here. So once you have a K inside in V, you can define one of these modules in terms of the subspace. So you do the same thing for each of these components. You have some kind of local causal modules. And assume, which is an assumption, it's something that happens in many geometric situations, and we'll see that later. Assume that all the components are linear. Then, if each is separable, then the projectivized resonance scheme, if you just view it in projective space, these are homogeneous varieties, so you projectivize. If each Lj is separable, then the components, or the scheme itself is reduced, and its components are disjoint. So it tells you something about the geometry of these resonance varieties. In general, they can be arbitrarily bad, but you put some mild restrictions on the components, and then you get this kind of global results. And conversely, if the projective resonance scheme is reduced and each Lj is isotropic, then all the components are separable in disjoint. Okay, again, so third, if each Lj is separable, then you can compute actually the Hilbert series of this causal module in terms of the local Hilbert series. Right, so, okay. And the final thing, so this is just separability. And then if you have separable and isotropic, which is kind of the best kind of situation that happens for hyperplane arrangements, for example, or at least conjecturally, this separability, then you have an explicit formula for the Hilbert series of the causal module in terms of some binomial coefficients. In terms of so you can express something which cannot be done in general in computative algebra. You can express the Hilbert series of a graded module in terms of the dimensions of the components of the support. Okay? All right, anyhow, so let's kind of finish the introduction, the setup. Now, where does this applies most of the time? To spaces, right? So if you have now, say, a finite type CW complex connected, then the cohomology algebra satisfies all those conditions, of course, with multiplication being the cup product. And then you can define these resonance varieties and support loci for the space X as being the resonance varieties and the support loci for the cohomology algebra. Okay. And there is a way to do this also on characteristic P, and there are some more sophisticated ways you can start with more information, not just the cohomology algebra. You can build in put a model, a DGA model, and then use also the differential and so on. But this is kind of the basic thing you can do to connect algebra with topology via the cohomology algebra. The degree 1, it depends just on the fundamental group. And then there are all sorts of applications. I mean, for example, they kind of provide the geometry of these varieties, of these resonance varieties, provide abstractions to the formality of the space, or one formality of the group. For example, if the group is one formal, which is going to be the case for the groups we're going to talk about today, which roughly speaking means that all the mass products in degree 2 vanish uniformly. Then the components are linear, which was, remember, the assumption I was putting on a previous slide. It comes from this geometric consideration from formality. But it also happens if for smooth algebraic varieties, for other kind of spaces, or even quasi-projective varieties, with maybe some other condition, you get this kind of linearity. Yes?
What happens if I consider the Steenrod algebra module action on the cohomology?
Well, good question. Well, that's why, see, then then you're talking about, this kind of jumbo psi with coefficients in where k would be Zima 2, say, or characteristic 2. And then you have the standard algebra acting on the cohomology algebra. The problem there is that, you see, it happens on the first slide. This is where I use characteristic 0. The only place I used here is here. Because, like, say the space is RP2, you get A squared equal non-zero. But then if you modify, you use the SQ1, and then you don't say multiplication by A. You say multiplication by A plus SQ1 of U. So you say delta of U is AU plus SQ1 of U. So you built in the action of the standard algebra. Then you can define the corresponding resonance varieties, and they have something to do with the orientability of the manifold. You get all sorts of kind of fun results using that way.
Probably not determined by phi 1.
Well, it's still kind of the low dimension, like R1. I still think it is, right? It's just to kind of use the two skeleton. But, okay, anyhow. So it has all sorts of applications to all sorts of geometric context and other kind of invariants in group theory and homological finiteness properties. But let me tell you a little bit, maybe come. Yes. Yeah, so via, there are also these characteristic varieties which are kind of jumbo psi for cohomology with coefficients in local coefficients, rank 1 local systems, also higher rank. There are these Bieri-Norman stable invariants which are jumbo psi for Novikov homology, or Novikov-Sikora homology. So you can connect these various type of jumbo psi, various constructions, for example, via tropicalization, and you get bounds and so anyhow, there is a whole theory there. I don't want to kind of, I cannot get into that. It would take me hours and hours, or days and days, or weeks and weeks to explain all that. So I just want to move on to tell you a little bit about what it has to do with group theory. So if you have a infinitely generic group, and you heard in maybe Taras, right? Is it Taras? You talk about lower central series, or maybe there was somebody else. Anyhow, so we talk about the lower central series, and the lower central series quotients, and you form an associated gradient Lie algebra. Okay, so you heard about all that. But also you can look at G modulo prime, right? The G modulo second derived subgroup, and take its associated gradient Lie algebra, which is called the Chen Lie algebra. And you define this invariance of a group as the Chen ranks, right? The ranks of GRK of G modulo prime. So the first example was computed by K.T. Chen in his thesis. So the free group, these Chen ranks are given by these binomial coefficients that you've seen on the previous slides, and this is not a coincidence. Okay, so with Dan Cohen, back in the day, we computed these Chen ranks of the Purebray group and got some kind of analogous formula. And, since then, kind of, what is the general phenomenon? And okay, so remember there was this Koszul module, W1, the first Koszul module of G, viewed as the gradient module over this polynomial ring. So about 20 years ago, with Papadima, we proved that if G is one formal, then you can actually compute these Chen ranks in terms of this, the gradient ranks of this module. Okay? It's not true in general. I mean, you need this formality in order to be able to make the connection here. So that's kind of the key hypothesis, and that gives you this formula. But, okay, so for example, arrangement groups or right angle acting groups, many other groups are formal, but then how to actually compute these Chen ranks? So it was a conjecture that I made, and I don't know, there is some more or less complete proof given by Dan Cohen with Hal Schenk. But then we revisited this. This is what we're trying to do, kind of, give a complete proof and sharper. So this is what we have now in terms of this result. If G is one formal, then the components are linear. We know that, but let's denote them by L1 and LS. So the assumption now, the extra assumption is they are separable and isotropic. So the easy one is isotropy. That's kind of easy. And the difficult one is to check the separability, which is connected, you remember, with the fact that the scheme structure is reduced. And in that case, the chain ranks can be computed by this formula, because these are we can relate this to that by the theorem I just put before. Okay, anyhow, so that's my introduction to the talk. Let's move on to simplicial complexes. So let me do now first like some preparatory material before I get into standard Reisner rings, having to do with, as you know, standard Reisner rings are reduced monomial ideals. So what I need in order to apply this theory, kind of a generalization of a notion of a reduced monomial ideal. Okay, so, and this goes back to work of Keiji Yanagawa from 2000, where you can define this notion of reduced monomiality to extend it to modules. Okay, so how do you do that? So first, let's put a multigrading on a polynomial ring by declaring the degree of xi to be, the i's basis vector for n to the n. Okay, and for an element a1, an, for an n tuple of natural numbers, you set the support as being the set of i's for each ai is greater than 0. So what's the definition? If you have now an n to the n graded as module, you call it to be square free. If for every multigraded tuple, multigrading tuple a, and any I in the support, the multiplication map that puts you from MA to MA plus EI, right, is an isomorphism. You see, for example, if you have K of X, right, and you have the ideal X squared, right, this is not reduced. You see how it fails, right? If you go from the degree 1 to degree 2, that map is not an isomorphism, right? Because X vanishes. When you multiply by X, you get X squared, which is 0. It's in the ideal, or it's in the quotient becomes 0. So anyhow, that's kind of the way to define in a slick manner the notion of having something reduced, okay? And then I is square free. It's an easy exercise if and only if it's a square free monomial ideal, or S mod I is a square free module, okay? So all these kind of notions are what you expect. And a free S module is square free if and only if it's generated in square free multi-degrees. Okay, so if you look at his paper, there is a bunch of results there, kind of, so extracting from that, that's what we need. So if you have a morphism, in this category of n to the n graded S modules, you have a morphism, and both of them are square free, then the kernel and co-kernel are also square free. And you have an exact sequence, and the extremes are square free, then the middle guy is also square free, okay? That's, none of this is very difficult, but if you don't know about it, I didn't think, this was the idea of this, Sammartano, who kind of joined this project and kind of made a case for this notion, which are very useful. We are trying to kind of do it in a different fashion, which was much more complicated. Okay, so as a corollary, so if you have a square free module, then, and you take its resolution, a minimal free resolution, then all the guys in the minimal resolution are again square free, okay? And if you have a bounded complex of free square modules, then the homology modules are also square free, right? You just take kernels, co-kernels, or exact sequences, you do all this homological algebra, everything stays within this category of square free modules, okay? All right, anyhow, so that's all that. All those remarks are in that paper from 2000. So what we kind of used out of that, kind of extracting of that, the following easy proposition that if you have a square free as module, then the annihilator ideal is also square free. So in particular, it's a radical ideal. It's equally so radical. Okay. You happy? Makes sense. I mean, it's all right. Okay.
Do you have some results on the dimension of M and the dimension of homology as well?
Yeah, I'm going to go to that, like a Casanova amount of regularity and projective dimension. We're going to get to that, okay? But I don't know whether it was in this original paper. It was kind of other motive. But the motivation of that paper, I mean, he starts, I mean, or maybe it's even the title, with it all came from Steiner-Reisner rings. Right. Okay, which is my next slide, okay? So just give me a little bit to get to that, okay? All right, so now everybody knows about this. We heard like maybe at least half the talks have mentioned the Steiner-Reisner ring. So I just changed the M to N, right? And K to delta, because K is already taken, so, okay? So let delta be a simplicial complex on N vertices, and I'm gonna look at a special type of polyhedral product, namely I take of the form zk of S1 comma point, right? So I take a subcomplex of the N torus by deleting the cells corresponding to the missing simplices in delta. And I write it as T delta because it kind of looks like a torus, a chunk of a torus, right? So this is a connected. It's actually, it's formal. I think this was Notbaum and Ray, maybe, prove that. And we did a one formality independently with Papadima, but they found the formality, it's also over Z formal. I mean, it has all, it's a, has all the properties you would like to have. It has dimension, you increase the dimension by 1, all right? Because the empty simplex corresponds to the base point. The vertices correspond to the circles and so on. And it's known to be K pi 1, KG1 if and only if delta is a flat complex. Okay, is this Mike Davis? I'm not sure who. Oh, Kim and Rush already before. I thought Kim and Rush computed cohomology. So yeah, I don't know. It's a bit. I think they computed cohomology, and Mike Davis and Rush China, I think, did the K pi 1. But okay, we can discuss the history separately. Well, okay. Oh yeah, glue K pi 1s again, K pi 1s and with injective maps. Yeah, okay, right. Everything goes back to Whitehead in that sense, yes. All right, and then the fundamental group is the right angle arcing group associated to the one skeleton. Okay, again, you saw that in Taras's paper talk. Now, he mentioned this associated gradient Liager being also a kind of a polyhedral product of sorts in this category. But I think the presentation is our paper, okay, from 2006. The ranks were computed before and they were recomputed, but I will not use the ranks here of the GRG, but I'll mention the chain ranks here. So we also proved there in 2006 that these gradient ranks, these chain ranks, are given by this generating series in terms of a certain polynomial associated with gamma, which involves the coefficients are given by looking at induced subcomplexes and computing number of components. And then you do some kind of shift or kind of a change of variables. Right, okay, just to make, I gave reference to all of this. I mean, you know, all this kind of stuff is included in these two papers. That the cohomology algebra is the external Steiner-Reisner ring, which I'll denote by this K Langer angle. Okay, I use square brackets for the usual Steiner-Reisner ring polynomial, and this is exterior with the usual description in terms of the missing simplices. Questions?
It's a recent theorem that determines the simplicial complex.
Right, well, define recent. I mean, I think it's maybe 10 years, 12 years. Yeah, but time flies.
It took a long time to do it.
Yes, no, it's a beautiful theorem, right, yeah, but yeah. Okay, so what are the cosumol? Let's go now through the, okay, so this is just a review, but let's do something new, right? Let's talk about the cosumodules of a simplicial complex. So I'm going to define it to be Okay, so in order to kind of, let's kind of build up a little bit. So let's start with the usual causal complex on variables x1, xn, which corresponds to, in the notation I had, L of the exterior algebra on V, where V corresponds to the vertex set. It's a K vector space. Okay, and terms of this complex are exterior power lambda I of V tensor S. And we'll do a multigrading, the obvious one, the degree of VI is EI. And so the usual causal complex is a complex of n to the n graded square free modules. Right? The boundary maps are just like xi, right? Plus or minus or 0. Okay, but now more generally for a simplicial complex, you apply this BGG functor, the left functor, to the exterior Steiner resonance, and you get now the causal complex of delta, which is a subcomplex of usual causal complex. And what are the terms are just the S modules generated by the vertices corresponding to the actual faces of delta. And the boundary maps are just restrictions. Okay? And then I define the causal modules of delta to be the homology of this causal complex, right, of delta. I mean, it could be a little bit, I mean, I'm using notation here a little bit because, you know, I define also the causal complex, resonance varieties, and so on for a space, but I'm not viewing delta as a space itself. I mean, a simplicial complex can have a crazy topology, right? Instead of using delta itself, I'm always working with the polyhedral product associated with delta, which is a much better space. It has no torsion in homology, it's formal and everything, as opposed to delta itself, which can be very difficult to analyze, okay? I mean, that's a separate problem. Okay, so this is, you know, putting together the theory we just kind of told you before. All these causal modules are actually square free S modules, right? I mean, it follows, you know, okay, what does it follow from? It follows from here, right? Because we're starting with this causal module, which is, where is it? No, it actually follows from the corollary. It follows the homology modules are square free modules, okay? So all we need this here, okay? Right, that's all we need, the corollary. And now let's look at we look at the resonance, okay? We need a theorem, a proposition for the resonance. Okay, now let's go back in time to, you know, about 20 years ago. So when we start looking at this with Stefan Papadima, we look at actually this apparatus, right? These resonance varieties of T delta of the exterior Steiner resonance. And then we got a complete formula, complete description. This is one of the few kind of classes of spaces in the literature where you can compute completely by explicit formula all the resonance varieties of the space. And here it is, okay? They're all linear, they're actually subspace arrangements, right? So the union of subspace arrangements. These are actually coordinate subspace arrangements. And they're given by some kind of Hochster-like formula, which ones you pick in terms of homology of subcomplexes. You know, the usual thing, right? But you have to kind of work it out in terms of links of subcomplexes and so on. Let me not go through it in detail now. It's a classical formula by now. But how about this R lower I, right? Those were not studied before, so this is the new stuff. So not only we can compute them, but also can compute the scheme structure and say it's reduced, right? So the decomposition in reducible components, it's actually simpler than for the other ones, you see. It's the same nature. You take, you know, subspaces indexed by certain subsets of the vertex set, but the condition is just vanishing of homology in 1 degree of the induced subcomplexes. You don't take links and various degrees, you see. The indexing set is much more complicated. You want, so there is a sigma in some degree for which, and there is a link in delta W of sigma. Okay, it's not the same condition. But in degree 1, you know that the two things should agree by the general theory, and in fact, you check that it's the same condition in degree 1, but in degree 2 and higher, they start to disagree. Okay, question?
You mean unions of coordinate subspaces?
Yes.
Their complements?
No, just union of coordinate subspaces. Yeah, yeah. On the other hand, this kind of the jumbo side, the apari, are not necessarily reduced with this fitting scheme structure that they carry natural, even in degree 1. So as sets, they coincide, but as schemes, they don't. So for the simplest example, you take a path on 4 vertices. This is the defining ideal, the fitting 0 of W1 of gamma. It has, these are the maximal primes, and this is an embedded component. It's got a fat point at the origin. Whereas the annihilator is just given by this intersection of these two ideals, which is reduced. Okay, all right. So let me just kind of go back to some work I did some years ago with Graham here and Sergei Uzvinsky, that we look at this propagation of resonance, for this apari. And then what we show that if the simplicial complex is Cohen-Macaulay over K, I think the definition, people use this definition during the talk, so let me not put it there. So Cohen-Macaulay implies propagation of resonance. So they get nested, right? R1 is equal to R2 and so on, up to the degree of the maximal dimension of the complex, and then they stop, they vanish. Okay? And that's kind of subtle. It has to do with, all sorts of, there are some topological reasons having to do with abelian duality, which is kind of a generalization of kind of an adaptation to this context of some notions of Bierry-Neckmann, okay? So instead of having vanishing, remember, Jan knows about this, right? Instead of taking vanishing of G with coefficient in ZG, right? Instead of going to the universal cover, you go to the universal abelian cover. And you mimic the Bierry-Neckmann definition. And then we show that this if delta is Cohen-Macaulay, then T delta has this abelian duality property, right? Okay, anyhow, so that's what's behind it. And it's still some converse is still kind of open, and there are some open questions that I will not go into that have to do with this relationship between these various notions in this context. Let me give you a quick example. Take now, again, all these examples are very easy. Instead of now path of 4 with 4 edges, with 4 vertices, I'm taking now just, wait a second, where am I? The disjoint union of two edges, right? Then, because this is disjoint, it's easy to see that the resonance is the whole thing, degree 1, right? When the graph is not connected, the resonance is the whole thing. You just cup product from one guy with another guy, you get 0 automatically, so the resonance is the whole thing. But R2 drops, it's a union of two coordinate subspaces, which are transversal. So you see, it doesn't propagate. Well, it's also not Cohen-Macaulay, otherwise you have a contradiction on the board.
Regularity must use the existence of a one-parameter family of generators, the regularity condition.
No, we don't.
One-parameter system.
Do you use that? I don't remember using that. Ask Graham. I'm rushing against time, right? I mean, I'm trying to finish. I still have some slides. So it follows that this R apari is the union of this lower J from J, because see on the upper resonance they propagate, whereas these guys do not propagate in general. But the question that this raises, I don't know how to answer it. I put this to the audience. So suppose delta is Cohen-Macaulay. Do the support resonance varieties propagate? Equivalently, do these two sets coincide? They do not in general, but how about for Cohen-Macaulay? And here is again an example where these guys do not propagate. It's the same type of example. Okay, so that's kind of connection with this work with Graham and Sergey. For graphs, all the formulas reduced to something much simpler. The resonance is just, you look at subsets of the vertex set for which the induced subgraph is disconnected. This tells you what are the components. There are coordinate subspaces, all again like before. And the coordination depends on the connectivity and so on. If this graph is disconnected, the resonance is the whole thing, as I said. But you see now this going back to this other work with isotropicity and separability. The bad news is that those conditions do not happen in general. Okay, so although the resonance is very simple, there are, this type of conditions fail. So you cannot. We computed the chain ranks by some other means, but it's not by that kind of chain ranks formula. And also we analyzed when are these spaces isotropic or separable. It's isotropic if and only if the subgraph is discrete, and separable if and only if it splits as a join. Okay? And then isotropicity implies separability for graphs as a consequence. Okay, now going back to your question about regularity and projective dimension and so on, I think that was more or less your question, but let me interpret it this way. We get bounds, okay? If delta has n vertices, then the ice causal module has regularity at most n, and projective dimension most n minus I minus 1. When gamma is actually a graph on at least 4 vertices, then the regularity is actually better. It's n minus 4 as an upper bound, and that's sharp because for a cycle, you get the bounds are attained. Okay. We also compute the multi-graded Hilbert series and the causal modules for an arbitrary simplicial complex. And they're given by this formula. You can compute, okay, let's just look here. You do this multi-graded Hilbert series for the causal modules of a simplicial complex, arbitrary, and are given by, again, computing homology of subcomplexes and doing some kind of clever generating series for that, okay? Do I have to explain that? I mean, it is a formula, right? Okay. And so this is my last slide. This is motivated. I think you gave a talk, or it has something to do with neighborly, right? And I said, okay, wait a second. We have a theorem. I forgot about it. So I added this. So suppose now the delta is, I don't know, d neighborly or d minus 1 neighborly. I'm not sure exactly what it is. So it means that the d minus 1 skeleton coincides with the d minus 1 skeleton of the full simplex. Okay? So for example, if the dimension is 2, you have a 2 complex, but then the 1 skeleton is the complete graph, and then you add some triangles. In that case, okay, here is a laundry list of all the terms you compute. You look at these causal modules and resonance varieties of delta. They vanish outside this range, and then we have presentations for WD and WD plus 1. There are only 2 causal modules you care about, and then the regularity is at most n minus 2. The 2 sets of resonance varieties agree in all ranges except the d plus 1, and RD plus 1 is either empty or the whole thing, whereas R upper D it has a whole bunch of components. Yeah. Okay, so that's it. Thank you.